Now that we have defined the concepts of distance and displacement, we can finally move on to the concepts of average speed and average velocity. Anytime an object moves a certain distance or displacement, it will do so in some interval of time. It's therefore useful to define the rate at which the object moves, which leads to the concepts of average speed and average velocity. Let's start with the average speed. The average speed of an object is defined as the total distance traveled divided by the total time interval. In words, we can write that speed is equal to total distance divided by total time. We can be a little more precise than this. We can use a mathematical form. If we define the speed to be v, the total distance to be d, and the total time to be t, then we get the equation that we have here that says v is equal to d over t. Now, what are the units of speed? Well, in the SI system, these will be the units of distance over units of time, which are generally meters per second. If we're talking about a larger speed, generally we use kilometers per hour. And in the British system, we generally use the very familiar miles per hour, for example, when we talk about the speed of a car. Now, the important thing here is that speed is a scalar quantity. That means that it's described only by one number, and it does not have a direction associated with it. The other concept is the concept of velocity. And velocity is defined differently. Velocity is defined as the total displacement divided by the total time. Now recall that displacement is a vector quantity. So in mathematical form, we can write, if we write the velocity as v with an arrow on top to specify that it's a vector, then this will be equal to delta x divided by delta t, where delta x refer to the total displacement. Now the units of velocity are still going to be the same as the units of speed because the units of displacement are the same as the units of distance. So it will still be meters per second, kilometers per hour, or miles per hour in the British system. However, notice that velocity is a vector quantity. That is, we need to specify a magnitude and a direction associated with it. And that's because displacement itself is a vector. So we're dividing a vector quantity by a scalar, and the resulting quantity is a vector. So we use the same letter for speed and velocity, but one is distinguished by the other by putting an arrow on top and specifying that it's a vector. So to summarize, even though speed and velocity have the same units, they represent two very different quantities. Speed is a scalar, and therefore it's always positive because the distance traveled can only be positive by definition. When you talk about distance traveled, you only care about how much you traveled from your initial position. You're not interested in the direction in which you traveled. Velocity, on the other hand, is a vector and therefore can be both positive or negative, depending on how we define the positive and negative direction of motion along our axis of motion. Also, and this is very important, average speed is not, in general, the magnitude of the average velocity, as we will see in the two examples that we're going to do now. So why do we talk about average quantities here? Because we're not interested for now in the instantaneous motion of the object, that is, the motion second by second, but rather we're interested only in the overall change over a certain amount of time. For instance, if you're traveling from Pittsburgh to Cleveland, which is, say, about 130 miles to make it round, and you do it in 2 hours, you will clearly say that your average speed is 65 miles per hour, because you travel 65 miles every hour, and in 2 hours you travel 130 miles. However, you're not traveling at 65 miles per hour for the whole trip. You might speed up, you might slow down at different times, but when you take the average over the entire time lapse, it's as if you were keeping a steady speed of 65 miles per hour throughout. So to understand this last point, let's consider the following example. We throw a stick at our Bernese mountain dog to fetch 5.45 meters away. the dog runs to the stick and back to us in 4.23 seconds. What are the average speed and average velocity of the dog? So here's a picture of the dog. Let's label a few things. Let's choose our direction of motion to be the x-axis. So this is the x-axis here, and this is the location 5.45 meters, and the dog is initially at 0 meters. So what does the dog do? The dog runs to the stick and back. So let's calculate the average speed first. What's the average speed? The average speed is the total distance divided by the total time. We're given the time to be 4.23 seconds. What's the total distance? The total distance that the dog travels is not 5.45, but rather double that, because it runs to the stick and back. So the total distance would be 2 times 5.45 meters, all divided by the time it takes a dog. And the time it takes a dog is, as it was given, 4.23 seconds. So when we plug in the numbers here, we're going to get, and I'm going to let you double check this, 2.58 meters per second. So as advertised earlier, the speed, the average speed, is a positive quantity. And in this case, it's just telling us that it's as if the dog was running at a steady speed of 2.58 meters per second throughout the entire trip. Now, what about the average velocity? Now, for the average velocity, we have to use the appropriate definition. The average velocity is a vector and is the change in position divided by the change in time. Now, the change in time is still going to be 4.23, so we can write that the total time is equal to the change in time, and it's 4.23 seconds. And the reason for that is that delta t is t final minus t initial, but generally t initial is taken to be 0, so this is just t final, which is 4.23 seconds. Now, what about delta x though? The initial position of the dog is this one here, and the final position of the dog is the same because the dog starts and ends at the same location. So the position vector for the dog initially and finally are equal to one another. So that is to say x final minus x initial divided by delta t is essentially x initial minus x initial, because x final is the same as x initial divided by delta t, and this is equal to 0 meters per second. So the average velocity has a magnitude of 0, and therefore we can see from here that in this case, for instance, the magnitude of the average velocity is not the same as the average speed. Now, in order to complete the problem, we have to do one more thing. Velocity is a vector, so we still would have to specify a direction. Now, this is the 0 vector, so it has no direction, but to be precise, we put an arrow on top specifying that that's the 0 vector. Let's look at a second example now. A marine biologist is trying to measure the swimming speed of a bottlenose dolphin. At time t0, one of the dolphins is 5 meters in front of her boat. At time 3 seconds, the dolphin is 10.5 meters in front of the boat. And then the dolphin does a backflip, and at time 5 seconds, is 8.75 meters in front of the boat. We want to calculate the average speed and velocity for the first 3 seconds, calculate the average speed and velocity for the whole 5-second interval, and then determine whether the speed is the same as the magnitude of the velocity in each case. This will really be a good time for you to pause the video and attempt the problem yourself, and then come back and look at the solution. Now, assuming that you've done that, let's see how we approach this problem. So first of all, we draw as usual our x-axis, and we're going to label the positions. And because there are 3 positions, instead of labeling them x initial and x final, I'm going to label them as x1, x2, and x3. So here's x1, which is 5 meters, and it takes place at time 0. And here's x2, which is 10.5 meters, and t2 is 3 seconds, and then sometime later is about here, which is x3, 8.75 meters at time 3 equals 5 seconds. All right, so the first thing that we have to determine is the average speed in going from x1 to x2. Now we have to determine this distance here. So let's call that distance d21. The distance in going from 1 to 2, that's clearly the difference between 10.5 and 5, which is 5.5. So d21 is 5.5 meters. Now, t21 will be really t2 minus t1, which is 3 minus 0, which is going to be 3 seconds. So what is our average speed in this case? Let's call it average 21. Well, it's going to be d21 divided by dt21, which is 5.5 meters divided by 3 seconds. And when we calculate this and round it appropriately, we get 1.8 meters per second. Okay, good. Now, what about the average velocity? Well, for the average velocity, we need the initial and final position. So v average to 1, it's going to be delta x to 1 divided by delta t to 1. And this will be x2 minus x1 divided by t2 minus t1. And here you can see that time, even though it's labeled differently, is still going to be the same thing. Now this is indeed the same exact expression, because x2 and x1, the position vectors, are nothing but that vector there that goes from x1 to x2. And so again, we get 10.5 meters minus 5 meters divided by 3 seconds, which is 5.5 meters divided by 3 seconds, which again gives you 1.8 meters per second. But we're talking about vectors here, so because this is positive, we have to specify this along the positive axis. But nonetheless, we see in this case that the average speed is indeed the same as the absolute value of the average velocity. And in this case, the two are the same because the change in position occurs along the increasing direction along the x-axis, and there is no change in direction, so the change in displacement ends up having the same magnitude as the distance. So this is a special case in which both the average speed and the magnitude of the average velocity end up being the same. But now what about the part 2? In part 2, we're asked to calculate the average speed throughout the entire 5-second time interval. So how do we calculate that? We need to also calculate how much distance the dolphin travels in going from x2 to x3. So that will be, let's call it d3(2), will be, because distance is always positive, the difference between 10.5 and 8.75, which is 1.75 meters. Recall, we're not worried about the direction here because we're talking about distance. and the total time going from 3 to 2 will be t3 minus t2, which is 5 minus 3. 5 minus 3 is 2. And so we can now calculate the total distance, d31, that is the distance in going from point 1 to point 3, as the sum of the two individual distances here. So is d2, 1, plus d32, which is 5.5 plus 1.75 meters, which is 7.25. And then the total time, clearly, is the time going from t3 minus t1, which we could get two ways. Either we can add this number plus that number, or just noticing that t1 is 0, t3 is 5, so this is just 5 seconds. So let me do that on the next screen. We have the two numbers. So the average velocity, the average speed in going from 3 to 1 is going to be this expression here, 7.25 meters divided by 5 seconds, which is 1.45 meters per second. So this is the average speed throughout the entire 5-second lap. What about the average velocity? We have to be a little careful here. If we go back to this picture, the average velocity is defined as the change in position, so the total displacement divided by the total time. So when the dolphin goes from x2 to x3, if we consider this to be a displacement, this will be a displacement in the opposite direction, like that. And therefore, we can say from the picture here that the total displacement of the dolphin in terms of vectors will be the difference of the green vector and the red vector. That is, we subtract the red vector from the green vector because they point in opposite directions, and therefore it will be the vector that goes from x1 to x3. So this would be the total displacement. We can also understand this by saying that x1 is the initial position of the dolphin, whereas x3 is the final position of the dolphin. So delta x for the entire 5-second lap is going to be x3 minus x1. So how do we calculate the average velocity in that case? The average is going to be delta x divided by delta t, and this will be x3 minus x1 divided by delta x. So this is going to be 8.75 meters, which is the final position, minus 5 meters, which is the initial position, divided by the total time lapse, which goes from 0 to 5. So it's 5 seconds minus 0 seconds. And when you plug in the numbers here, you're going to get a number that's much different than 1.45. In fact, is 0.75 meters per second. And what about the direction? If we look at the blue vector points to the right in the direction of the positive x-axis, and we can see that it's a positive velocity because the magnitude is a positive number. So we can say along the positive x-axis. So in this case, you can see in the second part that the average is definitely not the same as the magnitude of the average velocity as stated before.